Now, let us look at the forces which are to be considered. Okay. For that, first we will discuss how do we classify forces, and we classify forces as body forces and surface forces. We will discuss what are the characteristics with an example. Okay. The best example for body force is a gravitational force. Okay. We will keep that as an example and then see what are the characteristics of body forces. Okay. First, if you take a object, the origin of the force away from the object, let us say gravitational force acts on this control volume, it acts on its, but the origin is away from the object. Okay. And now the forces, body forces act on the control volume without contacting the object. The gravitational force is nowhere in contact with the object. So, origin is away, which of course leads to the fact that it does not force is not in touch or contact with the object. Okay. Now, it acts throughout the entire body of the object. The entire control volume is subjected to the force, and of course, that is why it is called a body force. Okay. So, acts throughout the entire body of the object, and because it acts through the entire body of the object, it is proportional to the volume of the object. Okay. If you say body force, gravitational force, for example, that is proportional to the volume of the object. Hence, you express body forces as per unit volume or per unit mass. For example, force is equal to mass into the gravitational acceleration, and what is g? It is body force per unit mass. So, if you write F is equal to m into g, F vector is equal to m into g vector. What is this of course, you can see g is acceleration due to gravity. What is the other way of saying? The body force F per unit mass will give you the expression for gravitation vector. Okay. So, body force expressed in terms of per unit mass, that is why you multiply by mass. Okay. Of course, example gravitational force, other body forces could be electrical force, magnetic force. Within the scope of this course, the only body force which we will consider is the gravitational force. So, to quickly summarize, body forces origin is away from the object, they are not in contact, they act throughout the body and hence proportional to volume and expressed as per unit mass. Okay. Okay. Now, coming to surface forces. Now, surface forces act through contact, body forces there is no contact at all, surface forces act through contact with surface. So, let us take an example, pressure force example for surface force. So, when you say pressure acts, it is in contact with the surface, it is not like it is without contacting have a pressure force. When you say moment, you say any surface force, for example pressure, it acts through contact with the surface either perpendicular or tangential, etc. Okay. In this case of pressure, it is perpendicular. Okay. Obviously, it acts on the surface of the object. In the earlier case body force, it effect was felt throughout the body, but for the case of surface force, it acts on the surface of the object. Okay. Now, because it acts on the surface of the object, becomes very obvious that it is proportional to the surface area of the on which it acts. Okay. Earlier it was proportional to the volume of the object, because it was felt throughout for the case of body force. So, this also leads to the fact that surface forces are expressed per unit area. Body forces were in terms of per unit mass, surface force because they act in contact on the surface and it is proportional to the surface area. So, you express per unit area. Of course, you are very familiar, pressure is force per unit area. Okay. That is how you get the unit of surface force as force per unit area. There are other surface forces, namely frictional force, reaction force. We will come across reaction force. What is the reaction force? Suppose if you have an object and you want to support it, and whatever force acted by the support on the control volume is a reaction force. Of course, frictional force is because of friction between the fluid flowing and the surrounding walls. Okay. So, we will come across all these kinds of forces in the applications when we discuss them. Okay. So, now what do? We express we write the integral form of momentum balance, and the right hand side now we have little more information. Earlier we kept telling that sum of all the forces acting on the control volume. Now we express that in terms of the body forces and surface forces. Okay. Little more detail than we have done earlier. This form of the linear momentum balance integral form, the forces are written more generically. Now since we have classified them, I express this in terms of body forces and in terms of surface forces. Okay. Now in this slide we will discuss about body force. As I told you, the body force which I am going to discuss is a gravitational force, and what is shown here is the control volume. For convenience, a sphere is shown and acted upon by gravity. Okay. This is for the surface force, which we will discuss in the next slide. Okay. Now how do you represent the body force in terms of expression? Now F gravitational force. So what do? I take the control volume, divide into smaller and smaller volumes. Okay. For as shown here, either the sphere is split into smaller and smaller control volumes, and then for each volume can have different densities, but now so which gives the mass of each element. But now we said body force acts throughout the object, and in this case because it is a gravitational force that is uniform for every smaller volumes. Okay. If you are considering electric force and magnetic force, it can vary based on the spatial location. Okay. So, because we are considering only gravitational force as the body force, I have not used here I. This I represents volume of the ith element, which can have its own density rho, but G is I have not used subscript for I for G, because the same gravitational force acts throughout the control volume, which means every smaller volume here is subjected to the same gravitational force. So, as usual we want to express this in terms of an integral. So, we consider many such volumes so small that this summation can be represented in terms of an integral over the control volume. Look at the limits is over the control volume, because it is a volumetric force or a force per unit mass, where it is a volume integral. So, how is the volume integral? So, rho dV will give you the mass multiplied by G will give you the gravitational force. Now because it is constant, we can take out of the integral sign, and what you have is integral rho dV, which is mass. So, the gravitational force is mass into the G vector. Okay. Now what is this mass? This mass includes the mass of the control volume, which means the shell, and mass of the contents of the control volume, both are included, because suppose I have to support this, I should support the weight of this container and also the liquid in it. Okay. That is why it says mass of the entire control volume. Of course, instantaneous, because the volume of liquid, let us say, that can vary as a function of time also. So, volume of the mass of the container may not vary, but mass of liquid in the container can vary. So, it says instantaneous mass of entire control volume. Okay, now let us discuss surface force. The surface force which we are discussing is the pressure force. Okay. Now we write the conservation equation, the linear momentum balance integral form of that, and we have discussed the body force, and now we are going to discuss the surface force. Okay. Now how do we express the force because of pressure? Okay. Let us look at this diagram. As I told you, it is shown as a sphere for convenience, but could be any object, and we are taking a small area there. Okay. So, let us take a small area and of area dA, and then this n vector represents the outward normal, always outward normal. So, if you have a taking area here, outward normal here, if you are taking area here, outward normal here. Okay. So, taking a small area on the surface, and if you are taking an area like this, the outward normal can vary depending on where you take the area. Okay. Now, I have shown pressure. Pressure is a compressive force. Pressure is a compressive force. What does it mean? It always acts into the control volume or onto the control volume. Let us say you have inlet here and outlet here, but still pressure will act in this direction, pressure will act in this direction, always onto the control volume. It is a compressive force, and that is what is shown here also. What is shown here is a pipe, and you have pressure acting into the control volume, onto the control volume. Similarly, here also pressure acts on the control volume, being a compressive force. Remember, our n vector is a outward normal, it is always pointing away from the control volume. If you have a inlet here, the n vector points this direction, outlet once again points away from the control volume. So, exactly their directions are opposite. Pressure always acts on the control volume, n vector is always away from the control volume. So, that is why n vector in this direction, the p vector is opposite to that. Okay. So, now what is that we are proceeding towards? We are proceeding towards expressing the force due to pressure over a small area. So, this is dF represents the force for a small area, and how do we express? What is the magnitude? Pressure into the small area dA. What is the direction? Negative of outward normal. Okay. That minus p dA n has in 4 terms in it, or the negative 3 terms in negative sign. Magnitude of force is p into dA, and then what is this direction? It is opposite to n, and that is why I have minus n here. Okay. So, p dA represents the magnitude and the associated direction opposite to n vector, that is why you have minus n here. Now, this is the force over a small area, we will integrate over the entire surface area. So, let us do that. The force due to pressure is equal to integral of minus p n dA. Remember, the integral is a surface integral, it is a surface integral. Why is that? Because pressure is a surface force, it acts over the surface, and so you are integrating over the surface area. To contrast with the body force acts over the entire volume, and the integral was volume integral. So, pressure being a surface force, the integral is a surface integral. So, this body force has volume integral, this surface force has surface integral. Okay. Now, let us integrate as they say above expression minus p. I have written n here because usually the variable is a, so I written dA at the end. Now, if you assume uniform pressure across the area, then you can take out this minus p n out, and what you will have is integral of dA, which is A. So, most of the time, or all the cases what we are going to discuss, the pressure is uniform across the area, either inlet or outlet. So, this simple expression will suffice for us, minus p n A. Now, okay, I just written whatever we discussed. Pressure being compressive force acts always onto the control surface, even with outflow, whether it is outflow, this is outflow, this is inflow, but always pressure acts onto the control surface. Okay, let us see how does it apply for the case shown here. Let us take the inflow boundary, the inlet. At inflow, the force due to pressure is given by this expression. What is that I have done? I have taken this expression, I am assuming pressure to be uniform, and this location is section 1. So, indicated P 1, the normal is outward normal, which means the outward normal is in this direction, it is along the negative x axis. So, n is minus I. The area I denote as A 1, the force is P 1 A 1, that is the magnitude. What is the direction? The direction is towards the positive x axis, that is obvious by intuition. The pressure acts into the control volume. So, the direction is towards the positive x axis, and that is why you have a plus I here. Okay, let us look at the outflow. What is the force due to the pressure? So, let us use the same equation. The location is 2. So, I used P2 here, and then now the outward normal is along the positive x axis. So, you have plus I here and of course, A2. So, when you simplify you get minus P2 A2 into I, which means the force due to pressure acts along the negative x axis. That is also correct by intuition. At the outlet pressure acts onto the control volume. So, it should act along the negative x axis direction. So, this force is P1 A1 I on the at the inlet. At the outlet the force is minus P2 A2 I. Okay. So, that is the significance of the negative sign. That negative sign ensures that pressure force due to pressure always acts into the control volume, and that is what we also took into account while writing the negative sign. Okay. So, this representation is important to remember. Now, as we have simplified the total mass balance, we will simplify the integral linear momentum balance, but not so much. I will tell the reason shortly. Okay. Now, we will start with the general form of the integral momentum balance. Of course, always working with x component. Okay. On the right hand side, we have body forces and surface forces. In the previous slides, we have seen how to express body force as a volume integral, how to express surface force as a surface integral. Now, if it is steady state, of course, the rate of change of momentum, that term is 0, and most of the time that term does not contribute, it is very negligible. So, all our examples we will consider only steady state integral momentum balance. Even if you look at books, most of the examples are on steady state momentum balance. That transient because of momentum change usually negligible. Okay. Now, as we have done for mass balance, if you assume in the inlet, outlet, etc., density, velocity is uniform, then I can take out this entire term outside the integral, and then you have integral dA, and that becomes A. So, you can simplify that integral in terms of summation. What does that summation mean? That summation means over all the inlet outlets whatever I have over the control volume. Okay. Whatever parts of the control volume where are part of the control surface, wherever inflow outflow is there, and I sum over all those surfaces through which there is inflow or outflow. Okay. So, from here to here assumption is the density, velocity are constant across the area, so that you can take out and write this way. So, as I told you, we are not going to simplify further. We, in the case of total mass balance, we had a series of simplifications. Okay. Here we may not understand also if we simplify, but how do we simplify and apply, we will understand directly when you look at the applications. Okay. So, that is why I am not proceeding and showing you a lot of further simplifications. How do we apply? We will straight away understand and understand better in fact when we go to the applications. Okay. So, we will stop with simplification at this stage. Now, we have this net rate of flow of momentum by convection term. If you take one particular surface inlet or outlet, this represents rate of flow of momentum by convection. What we will do now here is what is the sign of that particular term, and first observation is that two terms contribute to the sign. First is V dot n. We have seen that V dot n is positive for outflow, negative for inflow, and then V y can also be positive or negative depending on whether the y component of velocity is along y axis or against y axis. So, you have 4 combinations, the sign of V y and the sign of V dot n together determine the sign of this rate of momentum term. Okay. That is why we are discussing very specifically. In the case of mass balance, it is very simple, it is just V dot n either positive or negative, but here 4 combinations are possible, and that is shown using the control volume shown here, very nice representation from this book by Munson et al. On fundamentals of fluid mechanics. Okay. So, let us take there are 4 surfaces where there is inflow or outflow. Let us take one by one. First observation is that you have outflow here, inflow here, etc., and then inflow and then outflow. First observation is that n is always drawn as an outward normal, it is always pointing outside the control volume. So, n is away from the control volume. Similarly here, first observation. Okay. Now, let us take this surface through which there is outflow, because there is outflow, we know that v dot n is positive. Now, what is the direction of velocity? The direction of velocity is along the positive y axis, this is direction of y axis. So, the direction of v y is along the positive y axis. So, both are positive. So, rate of momentum as a positive sign for this phase. Now, let us look at this phase where you have inflow, because it is inflow, v dot n is negative, and what is the direction of velocity is towards the negative y axis. So, v y will be negative. Once again the rate of momentum is positive, because both are negative. So, either both are positive or both are negative, resulting in a positive sign for the rate of momentum through the whatever phase, either left hand side or the right hand side. These are individual rate of momentum for the respective phases. When you sum, you tell us net rate of momentum leaving. Okay. So, these are the, so for both the cases this rate of momentum term is greater than 0, so positive. Now, let us analyze for these phases at the bottom. This is the inlet phase, and because it is inlet phase, v dot n is negative, but what is the direction of velocity? It is along the positive y axis. So, v y is positive. So, you get a negative sign for the rate of momentum. Now, on the left hand side, for this case it is outflow, So, v dot n is positive, but what is the direction of velocity? That is towards the negative y axis. So, v y is negative. So, because one is positive, other is negative, this term, the rate of momentum is negative. So, we should be careful in arriving at the correct sign for this rate of momentum term. So, we will look at this of course in the application when you do look at the applications, but just to want to mention that in the case of mass balance it was very relatively easy, the sign depended on v dot n alone, but here it depends on v dot n and the direction of velocity as well, analogously for other directions, etc.